Okay, so today we're going to learn about sigma notation. It's not a new technique for calculating things. It's not really a new concept exactly. Notation is about how you write stuff down. So this is just a new way of writing things down that you already know how to write down in another way. It's a very compact way. Well, let me just tell you what it is. It is a short way to write a sum. And we've been working a lot with sums recently. At the end, I'll also do a little bonus thing. You see sigma notation a lot in science papers and a lot in computer science papers. Like if you want to know like what's all this machine learning about, like how do AIs work, and you look up a machine learning paper, is going to be full of sigmas because they're used a lot when you're talking about data. So I'll maybe tell you a little bit about that at the end. So here's the idea. Let's do the general version first, and then we'll do some examples illustrating it. It's a little bit weird. There's several parts to this, and it might not be immediately obvious what's happening. So what we're going to do is we're going to write a sigma, and then we're going to write an expression for the nth term of a sum. Or maybe not the nth term, but like the general term of a sum. And then down here you have a variable. And you tell the variable like a value it's going to start at and a value it's going to end at. And I know this doesn't make sense yet, but it will in like 35 seconds. So let's say that my general expression is I squared, okay? So I said this is a compact way of writing a sum. Here's the sum that it's going to be. I'm going to write several terms added together, and each term is going to look like I squared for a different value of I. So let's see, I is going to start at 1, so it's going to go 1, and then 2, and then 3, and then 4. So there's going to be 4 different terms being added together. So why don't you bracket out kind of 4 things that we could add together. And each term is going to be this expression evaluated for a different value of I. So I starts at 1, then goes to 2, then goes to 3, then goes to 4. And so now I ask myself, what is I squared when I equals 1? And it's 1 squared. And then what is I squared when I equals 2? And it's 2 squared. And then what is I squared when I equals 3? And it's 3 squared. And then 4 squared. So instead of writing 1 squared plus 2 squared plus 3 squared plus 4 squared, this notation means the same thing. And it's saying we're going to add up a bunch of these expressions for values of I that go from 1 up to 4. That's the idea. A student asks, how can you tell what I grows by? And the answer is I always goes up by 1. So the values of I here are pretty much always integers. I mean, you could extend this notation where maybe they're not integers, but I don't know if I've ever actually seen that anywhere in practice. I is sometimes called an indexing variable, and indexing refers to like putting a numerical ordering on a thing. So we're sort of saying we're going to start with 1 and go up to 4, counting by 1s, and that's like always what happens. Okay, so let's look at a couple other examples. Maybe I'll write them and you can decide what they're going to look like. So I'm going to scoot this down. All right, so go ahead and draw sigma. So your variable doesn't have to be I. You could have another variable. Let's call it k. So let's say k equals -3 to +1, and we're going to be adding up 2k minus 1. Go ahead and try and guess what the sum would be if you'd write it out, just as a way of testing yourself. Oh, ta-da! So what we've done here is we're saying, all right, k is the variable, and it's going to start at -3 and go up by 1 with each term until it gets to 1. So again, starting and ending. And then each term is going to be the expression 2k minus 1, evaluated at a different value for k. I've been writing the values for k underneath these brackets. This is just to help you learn. That's not part of the notation. So you wouldn't actually, like once you're good at this, you won't write that part. You'll just like know what to do. But if I do -3 times 2, that's -6, minus 1 is -7. -2 times 2 is -4, minus another 1 gives me -5. Let's do another one. So sometimes you might have a variable on top. Let's compare and contrast two examples. Go ahead and make like a little side-by-side thing like this. So sigma, let's go back to I because I like I. So let's say I goes from 1 up to n, and we're going to do I squared versus sigma I equals 1 to n squared. You would never actually write the one on the right, but students who are learning this sometimes get mixed up about what's what, and so students write this a lot. And so I want to sort of bring out how is this sort of wrong example, or like example that you wouldn't really ever do, how is this different than something that you would do a lot? I'm going to pause it. Why don't you try and say out loud to your neighbor, like, what do you think the difference here is? Go. Okay, here we go. So here, I goes from 1 up to n. You don't have to write that n is greater than 1. That's assumed from context. And sometimes sometimes sigma notation you'll see in books or articles, there's a lot inferred from context. So the idea here is we're going to evaluate I squared. So it'll be like 1 squared, 2 squared, 3 squared, and so on, all the way up to the largest thing where I takes on the value n. So rather than having a number here where I'd plug it in for I, we'll just plug in n for I, and n squared is the last one. So this is a compact way of writing a series where it's a general series. Like you're not going to specify the number of terms in advance necessarily. Let's contrast it with this side. Here, notice that the expression doesn't involve I. The expression only involves n, and n isn't changing. N is like a fixed constant. So here, I still have as many terms, like you can still say like what happens when I is 1, what happens when I is 2, and add things together. But the expression we're evaluating doesn't actually involve this number that's changing. So it's like the first term is n squared, and the second term is also n squared, and so on, all the way up to when I equals n, and that term also is n squared. So this is really just a way of saying, let's add up n squared a bunch of times. We could write this in an even more compact way. How many terms do we have here? Yeah, it seems like n. If I'd written 3 here, I'd be saying I goes from 1 up to 3. 1, 2, 3. If n was 5, I would be going 1, 2, 3, 4, 5. So it's sort of like if we're starting at 1, whatever this ending number is the same as the number of terms. So there's n terms. So what happens if I have n squared n times n cubed? Because that is n squared n times. So, you know, this is sort of a silly way of writing n cubed, which is why you wouldn't really ever do it. You would just write n cubed. This one, on the other hand, there is no shorthand, or like there's no like nice way of writing this out in a shorter way while sort of making the structure of the series obvious, except for the sigma notation. So this kind of thing you see written all the time. So I think I had 2 more things I wanted to show you. It's very common to use sigma notation for writing large polynomials. Remember what a polynomial is? It's like the sum of a bunch of powers of x. So like here's another example. If I wanted to write the series like 1 plus x squared plus ... plus x to the n. If you want to, why don't you, I'll just pause it and you can guess, like what would you fill in here, here, and there. So you can confirm your guess now. You can write, I usually use I as the variable, but you could use whatever you want. So I'm going to use the variable to represent the exponent here. So you might think about it this way, like 1, here's the 1, and then I'll add I starting with 1 going up to n, and then I'm going to evaluate x to the ith power. And so if you think about if I evaluate this expression for different values of I, I'll get I to the first power, and then I to the second power, and then I to the third power, and so on. And a student is about to say something really awesome. Video again. So I'd written 1 here because I was only writing this part as the sigma, and then the 1 and the 1 are the same on both sides. But students are noticing that 1 is the same thing as x to the 0 power. So really we could write this as sigma I goes from 0 up to n, x to the I, and now this single sigma expression is going to produce that entire polynomial. Okay, joys. The thing that you often see in textbooks, especially in calculus, you have occasion to think about a general polynomial. So here we have terms going up to n, but the coefficients are all 1. What if each of these terms has a different coefficient? So you could write it this way. You could say, like, the constant term is going to be a subscript 0, and then we'll have a subscript 1 is some other number times x, and then we'd have a subscript 2 x squared, and a subscript 3 x cubed, and so on, all the way up to a subscript n x to the n. So each of these different a variables is like a different number. That would be a different coefficient for that power of x. As you're experiencing right now, this is quite a bit of things to write down. So people often prefer to just say sigma I goes from 0 to n, a sub I x to the I. And this means the same thing, but notice that I'm using the I also to determine the subscript. You reminded me of a different thing, though. So if you have reason to, like, there's no reason why you can't, like, split sums up into 2 separate things. So, like, let's write a sum for just this part and then just this part. I could say, let's write a sum where I goes from 0 to 2. That's like a sub I x to the I. And then let's write another one where I starts at 3 and goes up to n. And, like, it's going to be the same thing. It's a little bit silly, because why wouldn't you just write them together? But the point I'm trying to make is, if you're adding a whole bunch of stuff together, there's no reason not to think of this as a chunk and this as a chunk being added. Like, that might be helpful, at some point in the future. It's just like a thing you could do. One last thing. So, sometimes in books or in my problem set, you may see the expression closed form equation. Or closed form, I guess you'd more frequently see closed form expression. What is a closed form expression? Anything that involves a ... is not a closed form. What closed form means is it means that you can evaluate it with a fixed number of familiar operations. So, for example, if I have the summation I goes from 1 up to n of I, this is not closed form, because what this is really telling me is I'm interested in the sum 1 plus 2 plus 3 all the way up to n. And this ... means that, I got to fill in the middle bit. So it's open form. It's not closed form, because to evaluate this, I have to do a different number of operations depending on what n is. A closed form version of this same sum would be if we actually used the arithmetic sum equation that we derived. So, if I were to write this backwards and sum and simplify, I would get that this same thing is equal to n plus 1 times n over 2. And this is a closed form of that same sum. It's closed because now to evaluate it, I only need to do like 1 addition, 1 multiplication, and 1 division, no matter what the value of n is. So if in a problem, if I say like find a closed form expression, what I mean is find an expression that doesn't involve any ... in it. That's closed form. Okay, last thing. I keep promising it's the last thing and then lying to you. very often in computer science articles, you'll see something abbreviated like this. So you'll see something like this where they'll tell you what the variable is, but they don't give you a starting or ending value. And this is just a way of saying, like usually in context, it's obvious what n is supposed to range over. So like you might have a data set with like 10 things in it. And so they're saying like, let's look at the sum of all 10 things in your data set. And so you'd see this in the body of the text. And I'm just warning you that this is a thing you might encounter. You'll see this and you'll be like, what is that? That's not what I was taught in math class. Well, like what you should do is just realize sigma means sum. This big E thing means sum. And then this is telling you what the variable is. And then based on context, you should be able to guess at what the things that are being added up are in the article. Okay, I think I am legitimately done now.